Hi everybody, my name is Puru Kuturi and welcome to Deep Learning Talk. Today we are going to discuss the paper Attention is All You Need. So before 2017, AI used to read the whole English language or for that matter any language word to word from left to right just like humans do. But then someone realized that that's not how you should read the language and that's not how you should model language because language is not necessarily sequential. It's not necessarily time series. We need to understand language as relational. Think of it like a database, right? So we introduced the idea of attention. Largely, we were facing a problem with sequential processing of language word to word, left to right. We started reading like human beings. We started reading each word from left to right. And then as we moved forward, we realized that we have recency bias. We are forgetting what we read 50, 100, 200 tokens before, right? And the memory in RNN was only able to retain the latest context. That's why RNNs had recency bias. RNNs were not able to remember long range dependencies. Also, since we are reading left to right in a sliding window format, RNNs were sequential. We needed a new idea to be able to understand language statistically, to be able to model language, and we wanted to do something different. We didn't want to model it sequentially. So, why does attention exist? What was introduced in the paper and why does it exist? Attention is all you need introduced the idea of attention. So why does it exist? It exists because previously RNNs were not able to model long range dependencies. We introduced something like LSTMs, BiLSTMs, GRUs with some memory to be able to model some long range dependencies, but we didn't succeed that much. Token 1 and token 150, the context between them was compressed and squished, and we were not able to model it nicely. We were not able to remember the context, and that's not how we wanted to do language modeling in a sequential fashion. The second thing was NVIDIA was introducing GPUs, and NVIDIA was advancing on the innovation of GPUs and parallel computation, whereas here the AI researchers or NLP researchers were stuck in sequential processing. We wanted to advance. We wanted to have a parallel processing, a parallel computing unit where we can understand the model, where our model can understand the language in a parallel context. So that's why we wanted to introduce a new notion of modeling language, which is attention. So to give you, to break the ice and to give you some insight on what exactly is attention, think of a sentence. Let's say the cat sat on the mat, right? It has a couple of tokens. Assume that one word is one token. Let's say that it is stacked horizontally. The cat sat on the mat. Let's say it is also stacked vertically. The cat sat on the mat. Now, what attention told us, or what attention instructed? Attention said, why don't you compute a score between every token to every other token? When I'm standing at cat, I want to know, let's say cat is my ith token. I want to understand out of all the jth token from the cat sat on the mat, which token should I attend to? What is the probability mass that cat should attend to mat? Cat should attend to sat. What is the contextual relationship between cat and mat? What is the contextual relationship between cat and sat? Right? So this is what attention is. Attention helps you produce a matrix, a simple n square matrix among all the two pairs of tokens to give you an opinion on how two words are contextually related, to let every word decide out of all the j tokens which token should it attend to, right? This is what the notion of attention was. So what is the intuitive mental model to think about attention? So the intuitive mental model is that we don't want sequential processing, we want global context. From between token 1 and token 100, I want to know the relationship between any two tokens. I want to treat a sentence not like a sliding window of words moving from left to right. I don't want to remember each word as I am saying it. Right. So this is what not to do. Now what to do? Build a global contextual matrix. Token 1 should have a score with token 1. Token 1 should have a score with token 2. Token 1 should have a score with token 3, and so on till all the tokens in the vocabulary. I want to build a global matrix. Now, every score will help me quantify the relationship or the contextual relationship between every two words. Now, every score will help me quantify the probability mass or the attention score or the contextual score, the relationship score between every two tokens. Right? This is what the intuition or mental model behind attention is. Right? For example, if I want to say we want to go and drop off the cash at the bank, cache is an embedding vector or a vector, a d-dimensional vector, right? In some d-dimensional hyperspace, cache is represented as a vector. Bank is also represented as a vector, right? What if I do a dot product between cache and bank? There is some sort of relationship between cache and bank. If I get the dot product, which is very massively high, that means the context or the relevance is very high. If the vectors are orthogonal to each other, which is they stand 90 degrees, since it's a vector and this is also a vector, they can each vector has direction and magnitude. If the dot product between them is zero, that means they are orthogonal to each other. If the dot product is largely negative, that means they are opposite to each other. If the dot product is largely positive, that means they're very similar, they're very relevant, they're contextually similar to each other, right? So the dot product between these two vectors will help me understand something, will help me build an opinion on which token among all the tokens will help me understand that token I should pay attention to which token J among the whole pool. Now, what is the formal decomposition of the whole attention mechanism? Attention mechanism depends on three things. One is key, query, and value. Before we talk about that, let's first talk about what do you input to the attention mechanism. What is it that we want that we can input to the attention mechanism? We want something like token embeddings. We want something like positional embeddings. Attention is global. Attention has no sliding window. We are not reading from left to right, but we need the ability to inherit positions. The cat sat on the mat. I want to understand that mat comes after cat. Mat comes after sat. I want to understand the relative positional ordering. So I need something like a positional embedding vector. Along with it, I also want to understand that cat is a vector in d-dimensional hyperspace, so which is known as my cat embedding, which is basically word embedding or token embedding. Every word is being treated here as a token. Just imagine one word, one token, right? Generally, one word is equal to one token is not largely true. A one word can have multiple tokens, right? A sub word can be categorized as a token, right? So, but here, for sake of simplicity, assume that one word is one token and every token is a d-dimensional embedding. Now, cat is an embedding vector, sat is an embedding vector, mat is an embedding vector. Obviously, the, on, and all of these stop words are also embedding vectors, right? So I need something known as embedding vectors or token embeddings. I need something like positional vectors or positional embeddings. I concatenate I don't concatenate, I add both of these vectors. When I add both of these vectors, now I have some information which contains the meaning of each word and which also contains the position of each word. This acts as the representation or the input to my attention mechanism or my attention sub. Now, the thing is, this whole representation that we built is going to be fed to a block or a sublayer. Let's call that sublayer the attention sublayer. So here we'll talk about three sublayers. One is the attention sublayer. The other is the feed-forward neural network sublayer. Feed-forward neural network, deep neural network, artificial neural network. It's all the same for now. And then residual and add normalization. So these are the three sublayers that we will have. The first sublayer that we are producing, that we are assuming, is the multi-headed attention layer. The multi-headed attention layer will take in input the vector, which is nothing but input vector or the combination of token embeddings, which is the meaning embeddings, the meaningful vector, and the positional embeddings, which is the relative ordering of positions. Both of them are d dimensions. That's why they can be added, right? Because since both of them follow the same matrix size. Now, why don't we have discrete sequence counter for ordering for positions, right? Because our model or our neural network does not really know how to do addition, how to really do subtraction in real time while training. We want a continuous space. We want some positional embeddings that have to be continuous in nature. Now, these positional embeddings can be trainable or they can be static. You can use sine and cosine functions to simulate or to generate positional embeddings. You can make them trainable. Whereas the token embeddings are always trainable. We don't use a static model to generate just-in-time embeddings. We start with embeddings that are not perfect, and then we train them. So all of the token embeddings that we use are trainable, right? They are not static. They're not generated from a model and then fed as input, right? So positional embeddings can be trainable, they cannot. They can be non-trainable. So there are both formats. In the attention is all you need, we use static positional embeddings that are produced from sine and cosine functions, right? So now the second block after we have produced the input is the attention block, which is nothing but the multi-layered attention block, which comprises of three things: query, key, and value. Now, to understand query, key, and value, since we are thinking of it like a search engine, now just imagine every ith vector's key says that I want to query among all the tokens j, that which token should I attend to, right? That's why we're thinking of it like a database, right? Every word, for example, let's say the cat. Cat will have its own key component, its own query component, its own value component, right? A WK, a WQ, WV, these three matrices represent the trainable weights of key, query, and value for each token, right? Now, for every ith token, you take the key. For every jth token, you take the query vector and you do a dot product to compute the similarity. Then you scale it down with the dimension, you do a softmax, you multiply it with the value to produce the attention score, right? So the intuition behind attention score is you use these three components: key, query, and value. Key basically says, what do I contain? Query basically says, what am I looking for, right? Value also says, what do I have that other people are looking for? What is my content? What is my information? This is the main abstract intuition behind all of these three matrices. And then these three are all narratives, these three are all matrices, nothing else. So you do a dot product between key of I and query of j to compute some similarity score, to compute an opinion or quantify an opinion on how they are contextually similar, how they are contextually relevant, to, to make a judgment that out of all the tokens j, which token should my ith token attend to, right? So it's like for loop within a for loop. Every ith token is searching for मैं किसको attend करूं, which token should I attend to, right? Now the mechanism of multi-headed attention says you build one attention matrix, which is build one matrix that is order of n square, that has contextual representation of every token I between every token j, between every two pairs of tokens. This is one such head. We say that build multiple such heads. One head represents one matrix. One head represents one sort of relationship, right? We want to capture syntax, we want to capture semantics, we want to capture multiple deeper hierarchical relationship in every deep neural network, in every neural network, whether it's convolutional or a normal deep neural network. We always want to capture hierarchical and information in depth, right? Here one head is capturing, for example, let's say the information between a subject and a noun. The other head is maybe capturing noun and a verb, then noun and an adjective. So we want multiple heads to fuse in a lot of information together. We concatenate all of these attention matrices that is produced by one head, and then we call it multi-headed attention, right? Now this multi-headed attention again gets multiplied with something known as WO, which is the projection matrix that combines all the information, which is also a trainable matrix. So here what all is trainable? Obviously the token embeddings are trainable, as we talked about earlier. The WQ, the query matrix, is trainable. The WK key matrix is trainable. The WV, the value matrix, is trainable. Then the WO, the projection matrix, this is also trainable, right? So these are all the attention components that are trainable. Then we have embeddings which are trainable, which is the token embeddings. Now, where does this output go? Now this output goes out of the sublayer, the attention sublayer, and it gets into another sublayer, which is known as the residual and add norm. Here we do some normalization, the scaling and shifting to stabilize training. We also add the residual. What is the residual? We again add input to the output of the sublayer, right? So basically we do, let's say, a function produced f of x as output. In the produced output f of x, we add an x to infuse in to infuse in the input, right? And then we normalize. So this is another sublayer that goes on after multi-headed attention. So after this, what do we do? After this, so we have multi-headed attention, we have residual and add norm. We go into feed-forward neural network. All of this information is combined and fed to the linear layers of a feed-forward neural network, or a fully connected neural network, or a dense neural network, or a deep neural network. Right now, that can also act as an output head that might help us in producing the output that we want. Right. So attention is all you need consists of an encoder decoder architecture. Right. Similarly, we have a decoder only architecture for GPT family. Similarly, we also have an encoder only architecture. Right. The larger difference between all of these architecture is basically the difference between an encoder stack and a decoder stack. In an encoder stack, you do all of the things that we discussed: attention, feed forward neural network, residual and add normalization, everything. In a decoder stack also, you do attention, feed forward neural network, residual and add normalization, everything. The large difference is decoder only stack helps us do next token prediction, helps us simulate the next token in the sequence. The encoder only stack only helps us produce the contextual representation. So the encoder only stack gets used in the BERT family, which is bidirectional encoder representation of transformers. The decoder only stack gets used in the GPT family. It uses something known as masking. So the idea of masking is, while you are computing the attention matrix, the order of n square matrix, it builds a triangular matrix. So generally, it is a lower triangular matrix. So basically, the cat sat on the mat. When I'm standing on at sat, I don't see the keyword mat. So you mask the future tokens. So just imagine we are reading from left to right, right? We are standing at 10th token. 10th token can establish relationship between 9th token. 10th token can establish relationship between 8th token, 7th token, 6th token, 5th token, 4th token, 1st token. But 10th token cannot establish relationship between 11th token because we've not seen it yet. We kind of mask the future. We kind of blur, de-signal the future. So this is what happens in the decoder only stacks, right? So this is the key difference in encoder and decoder only stacks, right? So whenever you read about transformers, so what exactly is a transformer? Now we're kind of deviating, but what exactly is a transformer? Transformer is when you combine all of these sub layers together. We heard the idea of attention, we heard the idea of residual and add normalization, we heard about the idea of feed forward neural network. When I stack all of them together, I build something known as a transformer. Right now, a transformer can be a decoder only transformer. If I'm masking, if I'm focusing on understanding the GPT family stack, it can be an encoder only transformer. If I only want to produce something which is known as the contextual representation between the whole language, right, between all the tokens, and I don't want to do next token prediction, that is my encoder only stack. If I want to do machine translation, English to French, French to English, I use something like an encoder decoder stack, which is mentioned in the paper. Attention is all you need, right? So if you want to understand all the three dimensions, it's worth reading the GPT-2 paper, the attention is all you need paper, and maybe something about the BERT family, right? So BERT space, BERT large, read the architectures of any encoder only transformer. One of the problems that I basically faced with attention, or I read about attention, is the computing power. So the other problem is that attention is language understanding, or attention is understanding the language. Attention is not really understanding the language. Like, I mean, the transformer does not really know that, there is something known as Paris, which is in France. It basically knows how to develop a relationship while training between Paris and France, between the contextual relationship between Paris and France. It does not really understand language like a human being, right? It does not have a biological neuron. But uh, on the other side, it also helps you develop contextual relevance, which helps you do next token prediction and simulate as if you understand the language, right? Now, the second failure, or the second trade-off, or the disadvantage for attention, is the computing power. As I talked about earlier, it takes order of n square time to compute one attention matrix. Obviously, it's a lot of time, because you in your vocabulary you can have a millions size token window, and computing attention matrix for a million cross million. Oh my god, it's not that easy. Obviously, in multi-headed attention we can compute each head parallelly, but computing one head also is a challenge in itself. It takes a lot of computing power. Let's also talk about where does this idea of attention sit in the deep learning stack. So it sits on top of linear algebra, since everything is matrix. Now it sits on top of neural networks, right? Since we are using a neural network inside it, we pass every output that we get from the attention sublayer to the feed forward neural network sublayer, right? Now it sits on top of RNNs, because recurrent neural networks were not able to solve long range dependencies problem. They were not able to solve the sequential processing problem. That's why it sits on top of that stack, right? So what do you need to understand to understand deep sequence modeling or attention? You basically need to have an idea of feed forward neural network, maybe a little bit of idea of recurrent neural network, right? And I'm assuming you would already know uh, Python, you would already know linear algebra, you would already know the fundamentals of the neural network phase, or whatever comes under the umbrella of neural network. Now, the last thing, what is the practical learning path? So I would recommend you read this paper once or twice at least. Now we have kind of discussed all the unknowns or the whole charter of the paper, the mental model that you need to understand attention. You go and read this paper at least once or twice. Try to implement attention from scratch. Don't use the PyTorch .NN module to implement attention. Build your own attention metrics. Maybe visualize uh, a heat map of your attention metrics. In Python, just take in the BERT model and use it to produce a attention matrix so that you can visualize the heat map and see what exactly attention is. Once you understand attention, then it's just basically stacking all the sublayers together and forming nothing but a class known as transformer, right? Then you will be able to understand, and you will also be able to fit it to a mental model of representational learning, where you will be able to correlate that, okay, this transformer has attention. Now there is another neural network which has neural network with convolution. So one is solving vision, one is solving deep sequence modeling. Now there's one more insight. It transformers helps us solve deep sequence modeling. Now, what if we start treating an image as a sequence? But how? We're treating language as sequences, right? What if we take a small sub patch, a small 2 by 2 patch, 3 by 3 patch of an image, and treat it as a sequence? Now every image is nothing but sequence of patches. If we treat an image as a sequence of patch, every patch can have a token. Every patch can be represented as a token, and every token can have its own embedding, and it can be fed to a transformer. This will give birth to an idea of nothing but vision transformer. I think that's it for now. Let's not make the video overwhelming, and I hope you like it. I hope you understand the mental models that we discussed in the video, and it helps you, implement attention faster. It helps you learn and read the paper. Attention is all you need. Thank you.